We're going to talk about the information covered, Chapter 5, Section 1. And this first lecture will be a fair amount of just sort of, I'll call it theory, although it's not really very difficult, but it's just a lot of definitions and having you understand some basic information about functions and what we're doing now. In math, they like to talk about relations or sometimes relationships. And the whole idea of a relation, especially in algebra, typically you have what we call an independent variable, which is usually x, and then you have what they call a dependent variable, which is y. For example, an equation is probably one of the most common ways that we express a relationship. The idea is, in this equation, we think of x as independent. We can set x to any number we want, but as soon as I assign a number to x, then y is going to be determined. The value for y depends on what I choose for x. If I say, well, let's set x equal to 1, then the value for y is already determined to be 3. So in this way, we like to think about x as an independent variable. I can make x whatever I want, but as soon as I decide or assign a number to x, then the value of y is going to be determined. So really, y depends upon the value of x. Now, in terms of the math world, the relation or relationship, in a sense, tells us how x and y are related. And actually, we're going to discuss the three different ways that relationships are expressed. One of them, the first one, we don't actually use all that much in this class, but the second, third one we use all the time. So I'm going to briefly describe 3 types of relationships that we use. 3 ways that we show how x and y are related. The first one is the simplest, and it's the one we don't use that much. They can give you a set, they can give you a set of ordered pairs, and that will define how x and y are related. So for instance, here's a set. A set is, this is an ordered pair, right, where the first number is your x, the second number is your y. What this tells us is, in this relationship, which we don't know what it looks like, we don't really know much about it, but all we know so far is that in this relationship, if x equals 1, then y equals 1. Sometimes they like to call this a set of ordered pairs. And you normally have more than a few ordered pairs. Say, for instance, I just sort of made this up. I have an ordered pair 2, 4, which means if x equals 2, y equals 4. And let's just do one more, just to keep it simple. 3, 7. If x equals 3, y equals 7. Now in a set like this, this is it. 3 ordered pairs. That's everything. In other words, based upon this set here, if x equals 2, what does y equal? Well, when x is 2, y is 4. If x equals 3, what does y equal? I go to the ordered pair that has x equal to 3, and I say, okay, when x is 3, y has to be 7. Here's an interesting question. For this set A, if x equals 5, what does y equal? We look up here. So I need to find an ordered pair that has a 5 in the x position. Here it's 1, here it's 2, here it's 3. So it turns out there's not an ordered pair where x is 5. So sometimes we might say this is like y is undefined. Maybe we'll write it like this. It doesn't exist. In other words, there is not an ordered pair where x is equal to 5. X equals 5 is not part of this set. As a matter of fact, let me go ahead and talk about a word you've maybe heard before. If I have a set of ordered pairs like this, they may ask me for the domain. The actual definition of domain is all the possible values of x. Well, the domain of set A, what are the possible values of x? There are actually only 3. The number 1, the number 2, the number 3. So for set A, let me write, the domain of set A equals 1, 2, 3. That's it. For set A, those are the only possible values of x. In other words, x equals 5 is not in the domain of set A. That's why I cannot do anything with it. So in the same way, domains look at the x's. They also ask us for the range of set A. The range are the y's. So I simply go up here and I say, what are all the different values for y? Looks like y can be 1, y can be 4, y can be 7. So I'm telling you, in this class, we are rarely ever going to do a lot of work with ordered pairs, but it's good to get a feel for how ordered pairs are a type of relationship that tells us how x and y are related. And if you're given a set with ordered pairs in it, you can always determine the domain and range. So I said there's 3 types of relationships. The second type of relationship will be something that you're very familiar with, and that's equations. Once again, a relationship tells us how x and y are related. We can write it 2 ways. In function notation, we would say f of x equals x plus 4, but we know if we want to, we can always rewrite it as, instead of f of x, we can put it y. So once again, an equation tells us how x is related to y. Now, unlike the ordered pairs, ordered pairs, sort of a very small, only 3 ordered pairs, a very small sort of universe, not much information. An equation has a huge amount of information, because in a sense, I can make x whatever I want it to be. If I set x equal to 0, y is 4. If I set x equal to 1, y is 5. If I set x equal to negative 1, y would be 3. And you notice I could go on all day long choosing values for x, and then I could go find my value of y. So an equation, once again, defines, tells us how x and y are related. And of course, if I wanted to, I could think of these as ordered pairs, but I won't get into that. So let's think about if someone says, what's the domain of this equation, and what's the range? Now this is where you ask yourself, when I look at this equation, is there some number that I could not plug into x? In other words, domain is what numbers can x be? Or an easier way to think about it is what numbers can x not be? This is an example where x can be anything. There's no limitation. We've already talked in class about the only limitation when you're looking at domain is if you have a variable under the square root, if you have x under the square root, or x in the denominator. We don't have any of that, so you could say all real. Sometimes it's that symbol, or as an interval, negative infinity to infinity. And in the same way, I asked what's the range? What could y be based upon what I choose for x? It can be anything. We'll just say this. Now the third type of relationship we oftentimes like to talk about is a graph. Once again, a relationship describes or tells us how x and y are related. So in other words, if you think about a graph, say I'll do a pretty simple graph, just a simple parabola. The idea is I can choose a value for x, say, I say, so when x is 1, what does y equal? I go to 1 on my x-axis, I go up to my graph, and I say, at this point, what is y? Y is 1. Say they said, okay, what about when x is 2? X is 2 is right here. I go up to the point on my graph, and I realize y is 4. One last one. Well, if I said, how about what happens when x is negative 2? Negative 2 is right here. I go up here. Y is also 4. How about domain and range of a graph? Very straightforward. The domain says, I'm looking at the values of x. I'm going to write an interval for my domain and ask myself the question, what is the smallest value of x for this graph? In other words, here's my x-axis. If I start heading way far as I can to the left, how far does this graph go? What's the smallest value of x this graph gets to? Well, this is a parabola, and although it goes up, it's also moving out. And it continues to move to the left the whole time. So basically, the smallest value of x for this graph is like negative infinity. This thing goes on forever. And if you think about the large, so this domain is going to be, the interval is what's the smallest value of x and what's the largest value of x. So how far does this graph move? This graph move to the right? What's the farthest out it ever gets? Once again, to infinity. Now the range, same idea. It's going to be an interval, except now I'm looking at the values of y. So I'm looking up and down. Look at my graph. What's the farthest down, the smallest number where this graph exists? Well, you notice when I go into negative numbers down here, the graph, there's no graph. The graph actually starts right here when y is 0. So actually I got to put a bracket here. And I say the range, the smallest value of y is 0, and it actually includes 0. So I put a bracket 0. And then I say, what's the largest value of y? How far up does this graph go? What's the largest value of y? Infinity. Okay, so those are the three main relationships that we have in math. Now here is the kind of thing they like to talk about in math. Doesn't always make sense, and I admit it doesn't always seem that important, but it's something you're going to need to know and you're going to be asked about. Relationships can be broken up into two categories. And here's a word you've heard before. So this is a case where in the math world they use the same word for two different purposes, and once again it can be confusing. Up here I call this function notation. We call f of x a function. Well, you know what's going to happen when we talk about relationships? Relationships can be broken up into two groups. The first one, many relationships actually are called a function, and I'll explain in a minute what determines whether it's a function. And then the other option, pretty obvious, not a function. So all these mathematical relationships we have, we can analyze them and determine is this relationship a function or is it not a function? And there's tests you can do actually. I'm going to show you in a minute. There's a test when you look at ordered pairs. If I look at this relationship and I say, is this actually a function or is it not a function? You can look at equations and say, is it a function or not a function? You can look at a graph and say, is this a function or not? So let's go over the three types of relationships, and let me tell you how you determine whether it's a function. First, if you're given some ordered pairs, you're given a set of ordered pairs, a relationship, and you're asked, is it a function or not? Here's the question you ask. First, you look at all values of x. So for instance, in a minute, we're going to look at this set here. So I'm going to leave room here because later on I'm going to add another one just to prove a point. Initially, 4 ordered pairs. I'm asked a question. We'll call this set B. Is set B, is it a function? I look at the values of x. 1, 2, 5, 7. Look at all the values of x and ask the question, does X repeat? In other words, do you have two ordered pairs with the same value of X? If the answer is yes, then it is not a function. If the answer is no, then it is a function. It's a very simple test. You look at all your x's, and if they do not repeat, you have a function. If they happen to repeat, it's not a function. So let's say, is set B, is this a function? Is this relationship a function? X is 1, 2, 5, and 7. Because the x does not repeat, we would say set B is a function. What's interesting, some of you may have noticed, look at my values of y, 2, 4, 4, and 3. And you say, well, hey, the y's repeat. But you know what? That doesn't matter. That has no impact on whether it's a function or not. The whole key is we're looking at the values of x to see if they repeat. Let me do another quick set. Here's set C. The question is set C a function? Look at my x's. 1, 2, 5, 1. You notice I have two ordered pairs with the same x, the x repeated. Set C is not a function. Now let me go ahead. Once you determine whether something's a function, so here's the idea. You start with a relationship, and they're broken up. Some of them are functions, others are not a function. Once you determine it's a function, then there's another thing you look at. Oftentimes in math they want to know, okay, it's a function, but is it a one-to-one function? And once again, there's only two possibilities. It is a one-to-one or it's not a one-to-one. So for instance, up here, we determined set B is a function, set C is not a function. Looking at set B, is set B a one-to-one function? How do we check for that? When you check for a function, the question you ask, does x repeat? Right? And we said, if x does not repeat, you have a function. If it repeats, it's a function. What's interesting, now if it's a function, the x's don't repeat, you go the next step, you say, okay, is it a one-to-one function? The question we ask then is, does y repeat? If the answer is yes, then it's actually not one-to-one. It is a function, it's just not a one-to-one. If the answer is no, then you have a one-to-one function. So for instance, B, we've decided B is a function. Is it a one-to-one function? Look at my values of y. 2, 4, 4, 3. Do the y's repeat? In this case, they do repeat. So I say, no, set B is not one-to-one. Just for fun, actually, let's go back to the one I did earlier. Let's go back to set A. First of all, let's set A a function. Look at my x's. 1, 2, 3. Since the x's did not repeat, it is a function. But then I say, okay, it's a function. Is it a one-to-one function? Now I look at the y's. 1, 4, 7. The y's do not repeat, so actually we can say A is a one-to-one function. All right, that's a lot of math definitions. Let's answer the same kinds of questions for equations and graphs. Let's actually do graphs second. We'll do equations last. So you're given a graph. That's your relationship. First question you ask, is it a function? In a minute, I'm going to show you what's called, on a graph, the vertical line test. Let me just show you now what the vertical line test is before I finish this. We'll look at two graphs. We'll look at an up and down parabola. And then we'll look at a sort of a side-to-side parabola. Vertical line test says you look at your graph and you can draw or imagine drawing a bunch of vertical lines, which means straight up and down, just all over your graph. Now, when you look at all those vertical lines, you ask yourself the question, does the vertical line cross the graph more than once? So let me give you the answers, then we'll look at these examples. If the answer is yes, it's not a function. If the answer is no, it's a function. If I look at this first graph, here's all my vertical lines, and I look and I say, is there any vertical lines, even just one, that crosses the graph twice? And you can see here, all these vertical lines only cross the graph once. So that means this is a function. We say it passes the vertical line test. Vertical line only crosses the graph once, it's a function. If I go down here, I look at these vertical lines, I notice like right here, it crosses the graph once, crosses the graph twice. If it crosses the graph more than once, it's not a function. So when you're given a graph, and you're asked, is it a function? Very, very simple to check. In your mind, you imagine a bunch of vertical lines, and you're looking for a vertical line that crosses the graph twice. If there aren't any, you've got a function. However, if you can draw a vertical line that crosses the graph more than once, you say it's not a function. Let's go to the next step. Maybe you've got a function and they say, okay, but is it a one-to-one function? So, for instance, this right here. We've determined it's a function. Now they're saying, is it a one-to-one function? To check for one-to-one function, interestingly enough, to check for a function, vertical line test, to check for a one-to-one function, you also then do the horizontal line test. And the same rules. If it crosses it more than once, then it's not a one-to-one function. So and once, not one-to-one. If a horizontal line only crosses the graph once, then it is a one-to-one function. So we decide this one's a function. I draw a horizontal line, it crosses it twice. It's a function, but it's not a one-to-one function. How about I draw a third graph? Is this graph a function? Vertical line test. It's only going to cross it once. It is a function. Is it a one-to-one function? Horizontal line test only crosses the graph once. This is a one-to-one function. And now for equations, which can sometimes be the trickiest. For the function question, you ask yourself, can one value of x give two values of y? Seems like sort of a silly question. If you look at this equation, if you think about plugging in x for 1, can you somehow get two different answers for y? Obviously not. So this is a function. There actually aren't very many examples of equations that are not functions. One that I can think of is what if I say y squared equals x plus 1? What if I set y equal to 1? Actually, let's do this. Let's do 1 plus y squared equals x. If I set y equal to 1, I plug in a 1 here. 1 squared is 1 plus 1, x is 2. Just for fun, what if I set y equal to negative 1? What's negative 1 squared? Negative 1 squared is 1. 1 plus 1 is 2. Look what I have here. I have the same value of x, but different values of y. So when x is 2, y can either be 1 or minus 1. I don't know which. Therefore, we would say this one is not a function. Now the next step. So this is just checking, can one value of, I should have put x. Can one value of x give two values of y? Then, one-to-one function, you ask the next question, can one value of y give two values of x? So the good thing is we don't have to use this very much, so I'm not going to spend a lot of time talking about this or give examples, but just so you know that you've seen it. Now let me go and stop here. I have one more little explanation to give of how to check, how to come up with an inverse function. But let me stop now, and I'll make that on a separate video.